and welcome. Today we're going to be talking about some aspects of power series convergence, and we're going to avoid all of the proofs involved in these power series convergence and instead approach this as more as a series of questions and just statement of some answers that help us understand a bit more of how power series work and what it means to converge and even more in what manner does some sort of power series where we write S of z, and usually we have a z naught there, is equal to the sum of n from 0 to infinity of some sequence of complex numbers times z minus z naught to the n power. All right, so this has a sort of domain of convergence. And we can usually write that domain as some sort of a z minus z naught is less than r. Okay? So those are their standard notation here. And for finite sums, we can write this. We can write Sn z naught of z to be equal to that truncated sum that starts at 0 and ends at capital N of an z minus z naught to the n power. Okay, so some questions then. So there's this notion, we've talked about it before, of absolute convergence. So absolute convergence is a strong type of convergence. So we've talked about some examples. Now, we had a theorem from before that says if, a series, if Sn z naught of z converges to some value, what we'll call the series itself, if this converges absolutely, that is, the series in modulus converges, if that is less than infinity, then Sn converges to S. Okay? So this absolute convergence implies convergence itself. But it turns out then that so there are points. So there are points. Are points z that are usually on the edge. I'll put that in parentheses, on the edge of our domain, where Sn does converge to n, but not absolutely. And so one perfect example of this is the log function z, where I'm going to expand about z1, and we found out that we have this series n plus 1 all over n of z minus 1 to the n power. Okay, so clearly if and our domain of convergence here is actually going to be, here's the origin right there, and we're expanding about the point 1, and we have to keep it, we can't have this domain touch 0, okay? 0 is not allowed, and so we have to keep that domain smaller than 0. But it turns out we can move it all the way out to 2. If I actually put z equals 2 in there, I see if I look at that, that becomes the sum of the alternating series n plus 1 over n, okay, which does converge. But if I look at this series in terms of its absolute convergence, it diverges. Okay, so that was at that point. But it turns out as long as we back away and we stay inside the domain, we can actually get we can actually state. So I'll just state that right here. So if z converges, sorry, if Sn of z at z naught converges at a point in the domain of convergence, then at a point, I'm going to call that point z1, then as long as z minus z naught is less than z1 minus z naught, right? I'm going to call then convergence, or I should say absolute convergence. Pardon me. I need it. Convergence implies absolute convergence. So what this really means is the implication goes both ways. Absolute convergence is convergence for power series, provided we're in the interior of our domain and not on the edge. Okay, so that's one way to state this. Okay, and really what we do is we're looking for points like z1 where it converges, and once we find a point where it converges at z1, then any point in the interior disk that's less than the distance away from z naught from there also converges. So, so what we're saying now is absolute convergence is synonymous with convergence, provided you're in some open set where on the boundary it's been established at some point that it converges. All right. So, so that's so in particular, our example of log z, which we had written down there before. We don't want to put that there. Like this, n equals 1 to infinity. Yeah, provided that z minus 1 was less than 1, this converges absolutely. But if z goes to 2, if z is equal to 2, then no, not true. It doesn't converge absolutely, and that's because we've already seen that alternating series in absolute value becomes the harmonic series, which is divergent. All right, so let's talk about some other aspects of convergence, and let's talk now about another aspect of convergence, which is there. So let's say I have some series, and it's centered about z naught, z. So I have this kind of thing. And I want to integrate this series. I want to now do some sort of contour integral. So this is, of course, converging to some function f of z. And I want to compute this integral dz over some contour. Okay, and we assume that C is inside the domain of convergence for our series. Okay, well, it turns out then we can integrate term by term, and that is I can write my contour integral. I can put in the series. And I can actually then pass the integral sign through this infinite sum and then get the following integral computed. So whatever that contour is, of course, this is an analytic function. If it's a closed contour, this thing is 0 because each term here is analytic. But this contour could be just anything, from point z1 to z2. or something like that. So whatever that integral is, you just compute the integral, and then you have the result. So you can do it term by term. So that is a nice way. And of course, that's the whole point behind series, is that we do some sort of divide and conquer. Now we have these individual components. Each one is very simple to compute. So now series does the job. So again, what we're saying then is it is legal to do so, provided that your contour is in the domain of convergence. Okay, so that again is just a really nice, piece of a very useful fact to have kind of in your front pocket as you're doing your calculations on analytic functions with power series. Okay, so another question is that of differentiation. So again, I have f of z, and it's analytic. And so, of course, f prime exists. In fact, all orders of derivatives exist. All right, the question then is, of course, if we have this as our power series, is going to be an z minus z naught to the n power, n equals 1 or 0 to infinity. Okay, the question is then, and then of course I can also look at f prime, which is another analytic function, all right, and I can expand and find its power series. All right, the question is that is it possible? The question then is it possible to, if I'm looking to look at this d dz, I'm going to do this operation. I want to know if I can pass, here's our series for f of z. I want to know if I can pass this derivative through the infinite sum. Certainly I can do it for a finite sum, but I want to know, can I do it for the infinite sum? In which case, I have, this becomes f prime, n equals 0 to infinity, and that becomes a naught, which is an, which is a constant, and then this times n, and then we have z minus z naught to the n minus 1 power. Now, of course, the constant term, we have to actually then start at n equals 1. So again, this is equal to b0 plus b1 plus b2. Oops, wrong. I forgot something. Z minus z naught plus b2 z minus z naught squared, ... on forever. And this is, of course, going to be a1 times n plus a2 times n plus, sorry, oops, made a mistake here. That'll be a1 times 1 plus a2 times 2, z minus z naught to the first power, plus a3 times 3 factorial. Oops, wrong one. That'll be times 3 z minus z naught to the second power. All right, so we see here, it turns out that yes, you can do this process of moving it in. You can do term by term differentiation. In which case, then, it implies then that b0 is actually equal to a1, and b1 is equal to a2 times 2, and so on and so forth. And what we conclude then from that is actually bn is equal to an plus 1 times n plus 1. Okay, so that's the relationship between the term, the coefficients in the original Taylor series and that of the derivative, and we can equate these coefficients just like that. Okay, so again, so now provided that we're in the domain of analyticity, we can do that. So another result is, of course, that what about S of n? So Sn of z evaluated at any point, this is going to be a finite sum. N equals 0 to an z minus z naught. And this is, of course, a continuous function. So a continuous function because each of its constituent parts is continuous. But what about, so, this, of course, converges to S of z at z naught, which is going to be the infinite sum. And the question then is this continuous? And the answer is yes. Okay? Yes, it is. For these power series, it is true. But why is this even a controversial question? And it turns out that other types of series don't have this property. Because you recall Fourier series. Fourier series, of course, operated on a completely different way of converging the series. It's a completely different method for creating a series, but it's another valid way to create a series. Fourier series, of course, is some series of the form where there's going to be some trig function times a set of frequencies times x, right? It's going to be something like that, and of course each one of those is continuous. But it turns out the infinite sum itself could converge to a discontinuous function. So with Fourier series, a completely different set of rules apply. They're a totally different scenario, and the reason why there's a difference is because the convergence in Fourier series is much weaker. And that's, of course, a good thing if you want to actually approximate functions with discontinuities, that you have this weaker form of convergence. But with Taylor series, we have a very strong type of convergence. We have this absolute convergence. We have this incredible type of convergence that will also guarantee that continuous functions can converge to a continuous function. Okay, so that is now established, right? And then the final thing we want to talk about then, the last question we want to really address is question: is a Taylor series about, or I should say of f about a point z naught unique? That is, if I have a set of coefficients an, does that define f of z on the domain of convergence? Or are there two sets of coefficients that both represent it? And the answer is yes, it is unique. It's unique on D, okay, on the domain of convergence. Of course, you could have another Fourier, you could have another Taylor series that has some overlapping domain of convergence, but overlapping, but has some other parts of it that are I should say it's you could have some other domain of convergence, another location in the plane where we have a different Taylor series where we could have different points. But if we're on that same domain of convergence, there's only one set of Taylor coefficients that defines f of z. Okay, and the same thing is true for Laurent series. i.e. S, and the question there is yes. Same thing there. There we have these coefficients an and also bn, and they uniquely define f of z on that domain of convergence, and that's very important. Okay, we could be looking in a different domain, in which case we'll have different coefficients. Okay, so I think that pretty much wraps up all of these aspects of convergence we wanted to discuss. Again, we didn't want to make any big proofs here, but just state these theorems so we have them in our front pocket. We know we can differentiate and we can integrate term by term. That's all okay. We know that convergence implies absolute convergence. That is, of course, a very, very, very good theorem to have. A lot of times we want to study absolute convergence, and to know that the series that underlies it converges, that's, of course, very useful. And then, of course, knowing that we have uniqueness allows us to then, of course, completely represent f of z by these discrete points, these discrete numbers, complex numbers. Okay, so with that all said, of course, we're going to move on to the next chapter. So thank you very much.